In this lecture, we will talk about matrix operations, specifically matrix addition and matrix multiplication. Suppose we are given a matrix A, which is of size m by n. That is, A has m rows and n columns. Such matrix can only be added to matrices that are of the same size. That is, matrices that have m rows and n columns. Suppose, for example, we are given the following m by n matrix A, which has entries A11, A12, all the way up to A1n in its first row, A21, A22, all the way up to A2n in its second row, and so on. Additionally, we are given the matrix B, which is also m by n, and has entries B11, B12, all the way up to B1n in its first row, B21, B22, all the way up to B2n in its second row, then these two matrices can be added to each other by doing component by component addition. That is, the matrix A plus B has entries A11 plus B11, A12 plus B12, all the way up to A1n plus B1n in its first row, then A21 plus B21, A22 plus B22, all the way up to A2n plus B2n in its second row, and this carries to the mth row where the entries are AM1 plus BM1, AM2 plus BM2, all the way up to AMN plus BMN. Matrix multiplication is a little bit more involved. If we are given a matrix A of size m by n, then this matrix can only multiply matrices of size n by k, and it can only be multiplied by matrices of size L by m. We will illustrate why this is the case in what follows. Consider a matrix A which is of size m by n, another matrix B which is of size L by m, and a matrix C which is of size n by k. The idea that an m by n matrix can only multiply an n by k matrix, and it can only be multiplied by an L by m matrix, is because we always want the size of the matrix multiplying the other matrix to end and begin with the same integer, in the top part with n and in the bottom part with m. The first product results in a matrix that is m by k, and the second product results in a matrix that is L by n. These are simply the integers that are in the exterior of the first product and in the exterior of the second product. Because of this restriction, the only possible products in this example are AC and BA. To perform this product, we split the matrix B into rows B1 all the way up to BL, and the matrix A into columns A1 all the way up to AN. The first row of the matrix BA contains the vector B1 dotted with every column of A. The second row contains the vector B2 dotted with every column of A, and the last row contains the vector BL dotted with every column of A. This results in L rows and n columns, meaning that the resultant matrix is L by n. Similarly, to perform the product AC, we split the matrix A into rows U1 all the way up to UM, and the matrix C into columns C1 all the way up to CK. The resultant matrix has entries U1 dotted with every column of C in the first row, U2 dotted with every column of C in the second row, and UM dotted with every column of C in the last row. The resulting matrix AC has m rows and k columns, meaning that it is m by k. Let's consider an example. Here the matrix A is 3 by 4 and the matrix B is 4 by 3. So the product AB is of a matrix that is 3 by 4 times a matrix that is 4 by 3, and the result is 3 by 3. Whereas the product BA is of a matrix that is 4 by 3 times a 3 by 4 matrix, which results in a 4 by 4 matrix. To perform the matrix product A times B, we consider the first row of A and take its dot product with the first column of B. This gives the first entry in the matrix AB, which is 20. The second entry is gotten by taking the dot product of the first row with the second column of B, and it gives 1. The third entry by the dot product with the third column, and it gives 19. The second row of AB is obtained by the dot product of the second row of A with all columns of B, and this results in 7, 5, 0. And the last row of AB is gotten by performing the dot product of the last row of A with all columns of B, which gives entries 10, negative 1, and 5. To perform the product of the matrix B times the matrix A, we consider the first row of B and take its dot product with every column of A. This constitutes the first row of the matrix BA, which is 4, 2, 11, and 6. The second row of the matrix BA is obtained by taking the second row of B and dotting that with every column of A. This gives us the second row, which has entries 2, negative 3, negative 5, and negative 6. The third row is obtained by taking the third row of B and dotting it with every column of A. Again, this gives the third row, which has entries 13, 1, 23, and 9. And finally, the fourth row is obtained by taking the fourth row of B and dotting it with every column of A, and this gives entries -4, 0, 1, and 6 in the matrix BA.